Okay, so we're going to look at question number 10 here. Now, part A is probably the easier part of these two. Part B is going to assume that we're going to be using the van der Waals equation. But we'll show you how to work all this out and how to actually even put it into our calculator. All right, so in A, it just wants to calculate the pressure in atmospheres of this container, assuming ideal behavior. Well, if we're assuming ideal, we're just using the simple applied ideal gas law, PV equals nRT, and we're just going to solve for the P. So our volume is 20 liters. N is 15.3 moles. R is our gas constant R, so 0.8206 liters, atmospheres, moles, and Kelvin. And finally, the temperature is 227 plus 273 to convert it into kelvins. Okay, bring up my calculator here, and we're going to go with 15.3 times 0.08206 times 227 plus 273. That's everything on the right, and I will just divide that by the 20 liters and get 31.4. If we go through here, moles cancel, kelvins cancel, liters cancel, so that's 31.4 atmospheres for our pressure. All right, now, technically speaking, nothing really behaves ideally, and we typically see that when we're at very high pressures or very high volumes, specifically at extreme conditions. So not volumes, very high pressure and very high temperature. And while neither one of these are especially high, it is going to be high enough that this is truly affected. So the van der Waals equation has a couple adjusting factors into it. One of them is the A. And actually, I'm going to write this equation slightly different than our book gives it to us, and I'm going to leave the A separate from those. It is multiplied by the n squared over v, and then the v is just n times whatever this b thing is. Now, these factors are based on the chlorines, and they do change based on what substance we're using, but we're going to use those and see how this affects the actual pressure. Now, it's not safe the pressure always does one thing or the other. In this case, it is actually going to go down, but it's not always. It's just more, it's different than that. All right, so n squared is the 15.3 moles, and the volume is 20.0 liters. So those two are used as kind of a fudge factor along with this A, and what that's going to do is those three things together are going to change the effect with regard to the pressure. They're going to add to that pressure. And now our V, actually we have our V, that is 20.0 liters. We have the N, and we have this B term, which is 0.0562 liters per mole. This is kind of a correction to how the volume is reacting based on the chlorine. And the nRT part is the same as this thing up above, so I'm not going to actually bother to write that out here. All right, but we are now going to solve this crazy thing for that, just that pressure. Longer process now, but our first thing is to do exactly like we did up above before we divide it by the 20. So the 15.3 times the R, 0.08206, and times the 227 plus 273, and we get 627. All right, that's here. So now I'm going to divide by the V minus MB thing. So I'm going to get it to the other side. So I'm going to divide by 20 minus the product of 15.3 times 0.0562. Now this is going to be close to that 31, but we haven't actually got rid of this correction yet. So now we're going to subtract this out. So subtract 15.3 squared divided by 20 times 6.49. And we get, no, I've typed something in wrong. Oh, I didn't v square. So I need to go back up here, get this value, and subtract 15.3 squared. This volume should be squared as well, divided by 20 squared times 6.49. That's better. So I should have had a squared here and a squared there. And my new volume is 28.999, so 29.0 atmospheres. All right. Now, for the most part, unless we're at very high temperatures or very high pressures, this value is going to actually be close to what the ideal gas law says. The ideal gas law gets us very, very close. And when we're at room temperature, it's almost dead on. The difference is way out 3 or 4 significant figures out. So most situations, we don't need to use the van der Waals equation. But when it's critical, it's worth the extra time to get a more accurate result.